Howdy, we're ready to start section 5.5. We're going to do some integration by substitution. We're going to look for ways to integrate things which are products that can't be undone by multiplication. Right now we know how to integrate expressions if we can rewrite them term by term using our basic antiderivative rules. For some products we'll be able to integrate by making a substitution and making the product integral look like a simpler integral. So it stems from the chain rule of differentiation. So let's look at the derivatives of some compound functions. When you've got the little parentheses holding the x squared plus 4x plus 9 to the fifth, remember we take the derivative by bringing the 5 down, raise the quantity to 1 power less, and then multiply by the derivative of what's inside. Similarly for our trig functions, we take the derivative of the outside rule first. The derivative of the sine of x cubed gives us the cosine of x cubed, and then you multiply by the derivative of what's inside. For our exponential function, the derivative of e to a power is itself times the derivative of the power. So if we wanted to find antiderivatives using the above examples, we know that the antiderivative, say of 5x squared plus 4x plus 9 to the fourth times 2x plus 4 is going to be the x squared plus 4x plus 9 to the fifth, plus that arbitrary constant. But now a lot of times we'll see it without this 5 here. So we know we can move numbers inside and outside of integrals. We also know we can do something to both sides of an equal sign. So what I'm going to do is divide both sides by 5. And what that says is that if I wanted to integrate, say, x squared plus 4x plus 9 to the fourth times 2x plus 4 dx, I do it by adding 1 to the power of the main part of the integral, the x squared, plus 4x plus 9, and then I divide by the new power. That's going to be our general power rule. If we want to integrate something that looks like a function of x to a power, where the derivative of that function is out here, next to the dx, you do it by adding 1 to the power and then divide by the new power. That looks kind of big and messy. I'm going to write it nice and short and concise like this. The integral of u to the n du is u to the n plus 1 over n plus 1 plus c, where the du represents u prime of x times dx. Oops, I said that was du. So we're going to look at our general power rule. In the next one, if you were to integrate the cosine of x cubed times 3x squared, the integral of the cosine of x cubed times 3x squared, here's the u of x, and here's the u prime of x times dx. We would integrate that as the cosine of u times du, where again, du is u prime of x dx. So that the integral of the cosine of u du is going to be, what do we get up here? The sine of u, where u is the x cubed. So in our example, u was the x cubed, so that's the sine of x cubed plus c. So let's add that to our list of integrals. If we're able to rewrite an integral as the cosine of u, we'll get the sine of u plus c. In our next example, the function part is in the exponent. So if you wanted to integrate this right-hand side, e to the cosine of x times minus the sine of x dx, you should get e to the cosine of x plus c. Now, if I took this minus sign out of the left-hand side, I would have to put it into the right-hand side. So what we're going to try to do is rewrite integrals of the form e to the u du, and we'll get e to the u plus c. So here the u was the cosine of x, and the du is minus sine of x dx. If I just have a sine of x dx, then my minus sign is going to have to be compensated for on the other side. So if we can rewrite all of our basic integral rules in terms of the variable u, where u represents a function and the derivative of the function is outside the parentheses, then we can use this integration by substitution examples. So let me show you from the beginning. We could integrate functions of the form where there's an inside part, might be part of a power, a trig function, or an exponential function. If the derivative is on the outside, then we can integrate with the method of substitution. So here we've got an inside part. I'm going to take u to be all of the inside. Okay, now we need its derivative. So u prime, I'm going to denote the u prime as du. So I take the derivative and I get 2x plus 4 times dx, right? U prime times dx is going to be the du. Well, that's not quite what I have up here. I've got an extra 2 in here. So to make these two match, I can do a couple of things. I can take the 2 out of here and move it over to the du, or put the 2 into the original equation and take it out with a 1/2. I'm going to take it out of here. I'm going to write du is 2 times x plus 2 dx, and then to make those two match, I'm going to move the 1/2 over with the du. And now I'm going to make these substitutions. The stuff inside the parentheses is what I called u. Then I've got the 5th power out here. And then the x plus 2 times dx is 1/2 times du. The 1/2 is just baggage. You can move it out in front of the integral. And now we've got our basic power rule, a variable to a power du. So you add 1 to the power and divide by the new power. And the last step is to put the x squared plus 4x plus 9 back in where the u is. And I can combine the 1/2 and the 6 and get 1/12. X squared plus 4x plus 9 all to the 6th plus c. And nicely enough, if you take the derivative of our little answer here, you should get exactly what we have as the integrand. So let's mentally try it. If I were to take the derivative of 1/12 x squared plus 4x plus 9, I bring the 6 down. 6 times 1/12 is 1/2. Then I get the x squared plus 4x plus 9 to the 5th times 2x plus 4. Now remember, I've got that 1/2 out front. Send it through the 2x plus 4, and you've got the integrand back that we started with. In the next one, the main part of the integral is the e to the power. So we're going to try to write that as an e to the u du integral. I pick u to be the cosine of x Then I take the derivative of that, and I get minus the sine of x dx. Right? du is u prime times dx. Now I don't want the minus the sign. I've got a positive sign in here. So I'm going to just multiply both sides by -1 and isolate the sine of x dx. And now I've got pieces for each trig function in my integral. I'm going to rewrite the cosine as u, and sine of x dx is minus du. Again, that's minus sign represents a factor of -1. I can pull it out front. Then when I integrate e to the u, I get e to the u, and u is cosine of x. And that's it. Again, take the derivative of that, and you'll get the original integrand back. The derivative of e to a power is itself. The derivative of cosine gives you minus the sign, and so that minus would multiply together to give you a positive sign. In the next one, the main part of the integral is the trig function, and so the compound part of this function is the x cubed. So we let u be x cubed. Maybe we'll take the initial step and isolate the main part of the integral and move the x squared over here. And we're going to hope that that becomes our du term. Our du is the derivative times dx. So I get a 3x squared times dx. Well, that's almost what I have out here. I've just got the additional 3. Let's get the 3 out of there by dividing both sides by 3. And there we have x squared dx is 1/3 of du. So let's make the du substitution. X cubed is coming out, and u is going in. X squared dx comes out, and 1/3 du goes in. After a while, you'll see that you can pull the constant out way at the beginning. I don't have to put this in-between step in. But then the integral of a sine is minus the cosine. So when I integrate this, I get minus 1/3 cosine of u plus c, where u is x cubed. All right, take the derivative. Hide the 1/3. Take the derivative of the cosine, and you'll get minus the sine of x cubed. Then take the derivative of x cubed, and you'll get a 3x squared. So if you multiply that by the -1/3, you get the positive x squared sine of x cubed that we had as the original integrand. All right, I've got a composite function here. I've got a square root, but it's a square root of an expression. So let's begin by moving the square root up as a power. Then we want to make a du substitution, where u is the stuff inside. Leave the power behind. Then the du term is u prime times dx. So u prime gives me a 3 times dx. But I don't have a 3 in the upstairs integral, so I solve this line down here for dx, and then substitute these two pieces in. This becomes u to the -1/2, and dx is 1/3 of du. The 1/3 comes out front. Now I'm going to use the power rule. To integrate a variable to a power, you add 1 to the power and then divide by the new power. So I'm adding 1 to a 1/2, and I get a 1/2. Then when I divide by a 1/2, I get a 2 out here. So now put it all back in terms of the original variable. Combine the constants to get 2/3 times 3x plus 2 to the 1/2 plus c. And if you're unsure of yourself, take the derivative of your answer. Make sure you get the integrand back. All right, we're just whipping through these. Number 5. We don't know how to integrate a logarithm, so that's the main part of the integral. Take that out, replace it with the letter u. Now we need the du term, which is the derivative of u times dx. The derivative of the log of x is 1 over x. And by gosh, that's what we have here. Let me separate these terms. I've got the natural log of x times 1 over x dx. So I have exactly what I need. Here is the u, here is the du. So we're integrating u to the first power du. Just your basic power rule. You get u squared over 2 plus c. And u was the natural log of x. Kind of fun, huh? I really enjoy doing these. Okay, a couple more here. All right, so let me set this up. I see the power is on the denominator. Let's move the denominator up and change the sign on the power. Make that a negative 3 power, and then put this other stuff out here next to the dx. So I'm kind of organizing it so that my integral looks like u to a power times u prime of x dx. That means the u has to be the longer polynomial. This integration by substitution always will work if the inside stuff is 1 degree more than the outside stuff, because I know a derivative brings the degree down. Okay, so u is x squared minus 3x plus 5. So the derivative of u is 2x minus 3 times dx. Well, when I look up in my integral, I don't have a 2x minus 3. I have a 6x minus 9. That means I need to squeeze a 3 in here, right there, so that I have 3 times du is 6x minus 9 dx. So you can take numbers out, you can put numbers in, as long as you do it to both sides. So this stuff outside the main part of the integral has to be the derivative of the inside, give or take a constant multiple. Now rewrite it. This becomes u to the negative 3, and 6x minus 9 dx is 3 times du. Again, the 3 comes out, and we're integrating u to the negative 3 du. That's your basic power rule. Add 1 to the power, divide by the new power. When you add 1 to negative 3, you get a negative 2. And so I can put those two constants together. And u is x squared minus 3x plus 5. And maybe you even like looking at that with positive powers. That's your personal preference. Okay? The stuff outside the parentheses has to have its derivative as part of the integrand, give or take some constant multiple. So let's set up the next integral. The main part of the integral is the secant. So let's write that first. Secant squared of the square root of x. Let's write that as x to the 1/2. And notice it's the secant that's squared and not the angle. Now let's think of that square root of x on the bottom as x to the negative 1/2 and put it next to the dx. So hopefully the stuff in the parentheses is the u and the du is the other stuff. So again, start with the stuff inside, the x to the 1/2. Then you take its derivative and you get 1/2 x to the negative 1/2 times dx. du is u prime times dx. Well, I've got the 1/2, the x to the negative 1/2 dx, but I don't have the 1/2. So let's take this line down here and multiply both sides by 2. so that we have 2 times du is x to the negative 1/2 dx. So now substitute in our integral, and we get the integral of the secant squared of u. X to the negative 1/2 dx is 2 times du. We can pull the 2 out front, and then integrate secant squared of u. Do you remember that one? The function that has as its derivative a secant squared is a tangent. So the integral of secant squared of u is the tangent of u plus c. Again, u was the square root of x. And there's our antiderivative. Okay. All right, so the next one. Well, maybe you've forgotten, but we don't have an antiderivative for the tangent. Let's take a minute before we do these last 2 examples and write down all of our basic integrals. So let me add a page and let's write our basic integrals as functions of u. And we're going to write u instead of the u of x, and du is the u prime of x dx. So we've got our basic power rule. Integral of u to the n du is u to the n plus 1 over n plus 1. Now we have our 6 trig functions. The integral of the sine of u du is minus the cosine of u plus c. The integral of the cosine of u du is the positive sine of u plus c. Then we had the integral of secant squared of u du is the tangent of u plus c. The integral of the cosecant squared of u du is minus the cotangent of u plus c. 2 more. The integral of the secant of u times the tangent of u du is the secant of u. The integral of the cosecant of u times the cotangent of u is minus the cosecant of u. Then we have our 2 transcendental functions. Remember that the power rule holds as long as n is not negative 1. But if n is negative 1, the integral of u to the minus 1 is our logarithm. The integral of u to the minus 1 du is the natural log of u. And remember, we put the u in absolute value bars so that these are defined in the same places. And then we have the integral of e to the u du is e to the u plus c. And then there are 3 inverse trig functions. The inverse tangent is going to look something like this. Whether I put the u squared in front or back of the 1 doesn't matter. They're added. So that's the arctangent of u plus c. The inverse sine and the inverse secant had square roots. The inverse sine has the variable behind a minus. And then the inverse secant had the square root sign, the squared variable in front of the minus, and the variable outside the square root sign. A lot of times we'll have this in absolute value bars in here so that they're defined in the same place. So our goal with this substitution is to make our integrals look like one of these. Sometimes it takes a few more steps. So let's back up and do the remaining two examples. What takes the additional step here is that we don't have an integral of the tangent of u. So what we've got to do first is rewrite that as the sine of 2x divided by the cosine of 2x. The trick here is to recognize that one of those trig functions is the derivative of the other. I've just got to know which way to place my u. When I look at this integral, I see a fraction. And when we have a fraction, we want most of the time u to be the bottom of the fraction. Most of the time. Sometimes you got to play around with it. So let's try taking the entire bottom of this fraction to be the u. So I'm trying to look at my integral like this. 1 over the cosine of 2x times the sine of x dx. 1 over u times du. Calculate the du. Derivative of cosine is minus the sine of 2x. Then the derivative inside gives me a 2. So let me rearrange that and write that as minus 2 sine of 2x dx. But when I make the comparison, I don't have the minus 2 up here. So we're going to take this line and divide both sides by that negative 2. Negative 1/2 du is the sine of 2x dx. Now let's go back up in here and replace the cosine of 2x with u. Replace the sine of x dx with a negative 1/2 times du. So you can pull that negative 1/2 out. There's one of our basic integrals. 1 over u du is the natural log of u. And go back and fetch u. U is the cosine of 2x. Okay, so again, we're trying to make it look like one of the integrals on that previous page. Now this next one is going to involve some double substitutions. Because notice if I rewrite this so that the main part, the 4x plus 1, is written first, and I'll put it to a power, and then the x dx, that stuff inside the parentheses is not 1 degree more than the stuff outside the parentheses. So we're going to have to do a little double substitution here. Watch this. I'm going to take u to be the stuff inside the parentheses as per usual. Then I calculate the du, which is the derivative times dx. Okay, so that leaves me with an extra x. It gives me a 4. I don't want the 4. Let's solve this for dx by dividing both sides by 4. 1/4 du is dx. So I've got something to put in for the 4x plus 1. I've got something to put in for the dx. I just have an extra variable. I need something in there as a function of u. And I'm going to get it from right here. I'm going to take that line and solve for x. To solve that for x, I subtract 1 and then divide by 4. Now let's put everything in here. Let's go down to this line right here. I'm going to put u in for the 4x plus 1. For the x, I'm going to put in u minus 1 over 4. And for the dx, we have 1/4 du. Let's take all those constants out front. 1/4 times 1/4 is going to give me a 1/16 out here. And inside I'm going to have u to the 1/2 times u minus 1 du. I still have a product, but in this product I'm able to distribute the factor outside. In the original problem I can't distribute that x through the square root sign. So let's distribute. Let's multiply this out. Bring it down here. U to the 1/2 times u, when I add powers, gives me u to the 3/2. Then minus u to the 1/2 times 1 is u to the 1/2. And now it's the sum of two basic integrals. I can integrate term by term. Add 1 to the power. 3/2 plus 1 is 3/2 plus 2/2, so that's 5/2. Divide, gives me a 2/5 out front. Add 1 to 1/2 and I get 3/2. Divide, gives me a 2/3 out front. And each u is 4x plus 1. So we can write our final answer is 1/16, 2/5 of 4x plus 1 to the 5/2 power minus 2/3 times 4x plus 1 to the 3/2 power plus that constant of integration. Now this double substitution is usually going to happen when the degree inside is not greater than the degree outside. Kind of a common trick to make your product integral a product that we can use multiplication, then integration. Okay, these take practice. And integration by substitution is something you've got to be very, very proficient at in Calculus 2. So practice them, and then practice them some more. And after a while it becomes obvious to you which part is the u and what you need to do to get